Hey everybody. Today we're talking about the chi-squared distribution, which is just a special case of the gamma distribution, where the parameter theta is equal to 2. Traditionally, the other parameter, alpha, is replaced with r, which is twice alpha. And there's good reasons for that we'll see in just a little bit. I've written the PDF here. It's a bit of a mess. Notice the presence of the gamma function in the denominator there. Of course, that's just a generalization of the factorial. Most of the time, you don't have to worry about the PDF of this too much when you're computing probabilities and so on. We use technology, as I'll show in just a little bit. We say that a random variable with this PDF has a chi-square distribution with r degrees of freedom. The chi-square distribution comes up all the time in inferential statistics, and a few of the most common places where you might run into it are in goodness of fit testing, testing the independence of categorical variables, or doing significance testing for variance, among many other applications. Very important fact is you're working to understand the chi-square distribution. If you have r independent, normally distributed random variables, so they all have z-scores, let's call those z1 up to zr, so those are the standard normal versions of those normally distributed random variables, then if you take the sum of the squares of all those z-scores, you get a random variable that has a chi-square distribution with r degrees of freedom. So in a sense, a random variable with a chi-square distribution is the sum of the squares of all those normal random variables with a standard normal distribution. I'm going to flash the proof for the simplest case, r equals 1, so the random variable x is just the square of a z-score, because I think this proof is illustrating some really important techniques that you may have use for in your statistical work, but I don't want to dwell on it here. Whenever we're trying to understand a random variable, we start with a CDF, the probability that x is less than or equal to a specified value, little x. Then I'm replacing the random variable x with what it's equal to, z squared, solving the inequality inside the probability statement for z, writing it as an integral using the distribution of z, the standard normal distribution, doing a change of variables, and at the end, getting the CDF of chi-squared of 1. Going back to the full expression, x equals z1 squared plus z2 squared, etc., if all of the normal random variables that are going into that sum are exactly equal to their expected value, then the value of the random variable x is exactly 0. As those normal random variables get further away from their expected values, the random variable x gets larger. So in that sense, if you have a random variable x with a distribution chi-squared of r, you're getting a measure of how far those r observations are from their expected values overall. And that's the idea that really goes into all of those forms of inference that I mentioned a little bit ago that are drawing on the chi-square distribution. The probability density function for a random variable with a chi-square distribution is skewed to the right, regardless of the parameter r. And its support is always just the positive real numbers. And this makes sense since x can be viewed as the sum of a bunch of squared z-scores. The graph of chi-squared of 5 is shown here. It's pretty typical. You can see it's strongly right skewed with support only the positive real numbers. When n is large, the distribution chi-squared of r is approximately normal, and you can already see that in the plot I'm showing here, which shows chi-squared of 50. But if you do look closely at this, you can see that there is still some skew in this plot, still some right skew. The expected value of chi-squared of r is just r. And I think this makes sense when we view chi-squared as z1 squared plus z2 squared all the way up to z sub r squared. So we're thinking about sort of the standard deviation of z-score being 1. As with any continuous random variable, we compute probabilities in a chi-square distribution using the cumulative distribution function, or CDF. And that represents the probability of randomly getting a draw from this distribution that's less than or equal to the specified value x. Visually speaking, I've shaded the area here to the left of little x to represent the value of the CDF, f of x, at that value, little x. The CDF is always evaluated using technology. I use R, where the command is p chi squared. And we have to pass it the value of interest and then the number of degrees of freedom. So for instance, to find the probability that x is less than or equal to 10 in chi squared of 8, we do p chi squared of 10, comma 8. We get about 0.725. And I've drawn an illustration of that probability here. All right, here's one for you to try. Compute the probability that x is greater than 8 in chi squared of 11. I recommend trying this before advancing it to see my solution. So we know the CDF, the probability that x is less than or equal to 8. So we're going to do the probability that x is greater than 8 using the rule of complements. 1 minus the probability that it's less than or equal to 8. That's 1 minus p chi squared, 8 comma 11, if we're using r. That's about 0.713. Here's one more. Compute the probability that x is between 10 and 12 in chi squared of 11. So again, give this a try on your own before watching my solution. So I'm going to do this using the CDF twice. I'm going to find the probability that x is less than or equal to 12. That's going to be p chi squared of 12 comma 11. That's going to give me the area under this graph to the left of 12. But of course, that's not just the shaded area. That's also the unshaded area at the left of this picture. So I'm going to subtract off the probability that x is less than or equal to 10. And that's p chi squared of 10 comma 11. That's the unshaded area on the left of this graph. Overall, I take the difference of those two p chi squareds. I get about 0.167.